Alright, now we're going to talk about 1.4 quadratic equations and applications, mainly focusing on the nature of how to solve quadratic equations, and we'll spend more time doing applications in class. So we're going to learn how to do solving equations in quadratic equations by factoring, extracting square roots, completing the square, and the use of the quadratic formula. So, we've already talked about factoring in a lot of cases, so I'm not going to go into that too much right now. However, extracting the square roots, or if I look at case number 1 right here, then it looks like all we have to do is isolate a, in which case take the square root of both sides, which means we will always have a solution that if there's a square equaling some constant or something else, then we can have it equaling positive or negative the square root, and that's because it's the second degree. The factors of this would be a plus the square root of b times the quantity a minus the square root of b, and you can test that out. Now, if we look at completing the square, one of everybody's least favorite methods, but albeit the most powerful, because it does lead to the quadratic formula. So there's only really two things that you really need to keep in mind about this. That if there is some lead coefficient other than 1, then you just simply divide everything by that number, okay, to start out, and ultimately end up with this. And if we end up with this, then we can proceed. And what do we mean by this? This is when a, the lead coefficient, is 1. Okay? So that means that we can complete the square. So the trick to doing this is to take 1/2 of the b, square it, and add it to both sides. Okay? And we'll do an example of that in a little bit. But regardless of what that b is, just take half of it, square it, and add it to both sides. That way we keep a consistent equation, and we can work on that. And let's talk about the quadratic formula real quick. And the quadratic formula, it really does come from completing the square, but I'll save you that for right now. And what it does is it does, again, solve for the intercepts, and that means that we just use this crazy looking formula here and making sure that we're in the standard form for a quadratic. We can plug in those values a, b, c, and calculate out our solutions. So if I looked at a very basic problem in which we were extracting a square, then what we could see here is that we have some square, so some square equaling some beast. In this case, it's 10. So that just means that all we have to do is take the square root of both sides. Now, I'm going to write it this way first, but I'm also going to write it with our exponential exponents, rational exponents. So it'd be the quantity x minus 1 to the half power, oops, I already beat myself to it, squared, and that equals 10. And the other way to look at it is by taking this to the half power and this to the half power. These are equivalent statements. These mean the same darn thing. But what I like about the secondary one is it's clear to see, very clear to see, why we have just x minus 1 left over, and we have the positive and negative square root of 10. And then in order to solve, all we have to do is add 1 to both sides, so that looks like we have x equals 1 plus or minus the square root of 10. So now let's move on to an example of completing the square. And notice that what we have here is the standard form for solving a quadratic. In which case we know that A is, well, let's not worry about that right now. The only one that we really need to worry about is B. Okay? And B in this case is a positive 5. Okay? And I'm going to do a little dotted circle around it just so you can see it. Now, all we have to do is get a perfect square to exist. So what we want to do, the first thing that we want to do here is divide everything here by 2. So that just looks like this. We'll divide that by 2, that by 2, that by 2. Okay? Now you'll see how the B is going to change. Okay? So now that we have this, what we have to look for now is x squared plus 5 halves x minus 4 is equal to 0. So now we just have to change the B to 5 halves. Okay, so we were given to it in standard form, but because the A was not equal to 1, we had to divide by 2. That changed our B, and now we can work with it. So what we're going to do is we're going to simply isolate the linear and the quadratic terms. So this right here is the quadratic, and this right here is the linear term. Okay? So what we're going to do is we're just going to do x squared plus 5 halves x, and that will all equal 4. So we just add 4 to both sides. Well, let's change that. Okay. Now, watch what I'm going to do. I'm going to take something, I'm going to take half of it and square it. I'm going to also take that same thing, take half of it and square it. And now what is that half thing? Well, it's just that right there, the B. So that is going to be substituted in. So that'll be 5 halves divided by 2 squared, and then it'll be 5 halves divided by 2 squared. So we're really taking a quarter of 5, right? But what this does is it makes it really easy for us to get the perfect square. Because now, as you can see, we have a perfect square. So that just means we take down the base, and I'll let you see where I came up with this, but I'm going to take the base on x and the base here, and that's going to come into what? Well, that's going to come into 5/4, and now I can square it. Well, where did I get the 5/4 from? Well, 5 halves divided by 2 is the same thing as 5 halves times 1/2, which is 5/4, just in case. So we're going to leave it in that form, but now we're just going to calculate this out, which is plus 5/4 squared. And now you can notice that what did we do? We isolated x. Okay? So all we have to do is do some number crunching. So let's do that first. Well, that's going to be 4, and that's just going to be 25/16. So if we change this 4 right here to having a denominator with 16, then that just means that we have to multiply 4 by 16 and get 64. Okay? And then we just set everything equaling it back and do the final number crunch. And remember, that's why we needed the common denominators, was just so that we could add the numerators. So it looks like what we're going to have is 89 here. And now the only thing we have to do is take the square root of both sides, or, you know, raise to the half power both sides. So what I'm going to do is I'm just going to use that classic way here and get x plus 5/4 is equal to plus or minus, well, the square root of 80, oh, not 80, 89, all divided by, well, what's the square root of 16? 4. So now, if we wanted to solve, we could do some stuff maybe with the 89, but let's not worry about it right now. Let's just continue to isolate x. So that just says that we have a positive 5/4 on the left, so on the right it'll be negative, or x is equal to negative 5/4 plus or minus the square root of 89/4. Or another way to represent it, right, is if we could just, now that they have common denominators, so this would just be negative 5 plus or minus the square root of 89 all divided by 4. And I'll leave that up to you right now to check. Okay. So that's what it looks like, what we have. Alright, now let's look at an example. Well, we'll use the same example actually, but we'll solve it using the quadratic formula, which I have nicely located up here. So luckily for us it's in standard form, and all we have to do is make a nice little list and identify what A, B, and C are, and we'll use different colors for these. So A is 2, we'll use red, and well, B is 5, we'll use blue, and we'll use hot pink for negative 8. Now, be careful, remember that the standard form is ax squared plus bx plus c is equal to 0. So, ideally all we're doing is taking that negative 8, okay, that we're adding. So now that we have the list, all we have to do is do our substitution. So we can find out the x-intercepts if, and notice what I'm doing. I'm just going to pull out all of the variables, and I'm just going to make the parentheses where everything should be. And I should draw this out a little bit more here, and make that all divided by 2a. So now all I have to do is substitute a's where a's go, so looks like 2 and 2 go down there, and blue for B looks like it's going to go here and here, and then the lone C looks like he'll be right here. So now all we have to do is number crunching. Not very fun, right? But this is just going to be negative 5 plus or minus the principal square root of 25 plus, well, that's going to be 32. That looks like 64 all over 4. And if we crunch this down, negative 5 plus or minus the principal square root of 89 all over 4. So we have 2 intercepts again. And just so you can see how we could, write these as what they are, because they are x-intercepts, we could write one as the negative counterpart as negative 5 minus the square root of 89 over 4, comma 0. And we could write the other one, which is the more positive version, negative 5, or it could be, but if you see what I'm trying to write out here, comma 0. So we're just taking that positive and negative version of it. Alright, so we'll do one solution by factoring, and I made one that wasn't in standard form, or I picked one that wasn't in standard form, so we have to rewrite it in standard form. which just means that it's going to be negative 2x squared, and then we can say it's plus 5x plus 3, and that is equal to 0. And now what I'm going to do is I'm going to factor out a negative 1, just so we can make it easy. So we have 2x squared minus 5x minus 3, and have that equal to 0. And now we're going to find the product AC that is going to combine to give us negative 5. So that just means that we're going to take 2 times 3, or these numbers here, and don't worry about the signs for right now. The only time that we really care about the signs are when we're ready to combine. So if I draw this out here, and we list all the factors of 6 that have a potential. So let's just go 1, 6, 2, 3, okay? So all we have to do are find the ways to combine any of these values to get to negative 5. Well, it looks like we can use both of them. However, it's not as clear. We cannot use negative 2 and negative 3. Why can we not use these? Because when we multiply a negative 2 times the negative 3, we're going to get the positive 6. And ideally, remember, that product AC is really negative, okay? But I told you not to really pay attention to it until this point. Now it's very easy to see that we can use a negative 6 and a positive 1. So if we rewrite this as, I'm just going to rewrite the whole thing here as it was. And now what we're going to do is break that 5x into 2 nice and easy numbers, which we have here, which is the negative 6x plus x minus 3. Now what we're hoping is that we can factor by grouping. Okay? So if we cut this right down the middle here, and we realize that over on the left-hand side of that cut, we can factor out a 2x, then that leaves us with x minus 3. And then let's use a different color, the black. So, and then what we have left over is x minus 3 quantity. Now, I'm putting the parentheses around this only to denote that when I factor out the quantity x minus 3, 1 still remains. Okay, and that all equals 0. And now what we have is the quantity x minus 3 times 2x plus 1 equals 0. And now we're going to apply the zero product property, which just says that x minus 3 has to equal 0, or 2x plus 1 has to equal 0, or both of them. So it's like the inclusive or. So in this case, x is equal to 3, and in this case over here, x is equal to negative 1/2. And I'll let you check those.